ครับเดี๋ยวเราจะเข้าสู่บรรยากาศวิชาการกันนิดนึงนะครับแต่ว่าจะลดความเป็นทางการลงนะครับครับเรียนเชิญด้านหน้าเลยนะครับที่ด้านหน้าว่างนะครับฝั่งนู้นก็ยังว่างนะครับฝั่งด้านนี้ก็ยังพอมีที่นะครับโอเคครับผมขออนุญาตเริ่มเข้าสู่บรรยากาศวิชาการเลยนะครับกราบเรียนท่านคณาจารย์นะครับท่านนักวิจัยนักศึกษานิสิตและนักเรียนที่น่ารักทุกคนนะครับผมรองศาสตราจารย์ดร.นิมิตรนิมนะครับ
and I'm Assistant Professor Dr. ทศพรทองจันทึก
ครับยินดีต้อนรับทุกท่านเข้าสู่บรรยากาศวิชาการนะครับกิจกรรมนี้เป็นหัวใจของการประชุมวิชาการทางคณิตศาสตร์ประจำปีพุทธศักราช 2569 นะครับตามที่ทุกท่านทราบแล้วนะครับว่าครั้งนี้เป็นครั้งที่ 30 นะครับโดยกิจกรรมนี้นะครับจัดควบคู่กับการประชุมวิชาการทางด้านทฤษฎีจำนวนนะครับแล้วก็จัดควบคู่กับ The International Session on Nonlinear and Convex Analysis ในวันนี้นะครับหลังจากที่ทุกท่านได้ร่วมพิธีเปิดนะครับแล้วก็ได้ถ่ายภาพอย่างสนุกสนานกันแล้วนะครับผมขอนำพาทุกท่านเข้าสู่บรรยากาศวิชาการกันเลยนะครับภายใต้ธีม Mathematics Building Pathway to the Future ครับ
Welcome everyone back to the main keynote sessions of the 30th annual meeting in Mathematics 2026 and Conference in Number Theory and Application 2026 in conjunction with the International Session on Nonlinear and Convex Analysis. As our opening is concluded, it's time for our exciting journey under the theme Mathematics Building Pathway to the Future.
ครับผมขออนุญาตอัปเดตภาพรวมของกิจกรรมในวันนี้ให้ทุกท่านได้ทราบก่อนนะครับในช่วง Keynote Session เช้านี้นะครับเราได้รับเกียรติจากวิทยากรผู้ทรงคุณวุฒิ2ท่านด้วยกันนะครับเราจะเริ่มต้นด้วยการบรรยายของท่านแรกนะครับในช่วงเช้านี้ก็คือการบรรยายของท่าน Professor ดร. Jakob Stix นะครับจาก Goethe-Universität นะครับประเทศเยอรมนีนะครับหลังจากนั้นนะครับจะเป็นการบรรยายในเซสชันต่อไปนะครับเซสชันที่2ของท่านศาสตราจารย์ดร.สุเทพสวนใต้จากมหาวิทยาลัยเชียงใหม่นะครับผมคิดว่าในวงการคณิตศาสตร์ทุกท่านน่าจะรู้จักทั้งสองท่านเป็นอย่างดีนะครับรับรองครับเนื้อหาทางวิชาการเข้มข้นแน่นอนครับ
Just to give you a quick heads up for this morning, we are very honored to have two distinguished keynote speakers for today. In just a moment, we will begin our first session with Professor Dr. Jakob Stix from Goethe-Universität Germany. After that, we will move on to our second talk by Professor Dr. Suthep Swantai from Chiang Mai University. So please stay tuned for these two fantastic and exciting talks.
ครับและเพื่อไม่ให้เป็นการเสียเวลานะครับสำหรับการบรรยายในเซสชันแรกของ Professor Dr. Jakob Stix นะครับในตอนนี้ผมขอกราบเรียนเชิญท่านผู้เชี่ยวชาญนะครับที่จะมาทำหน้าที่ Chairperson ของเรานะครับขอต้อนรับท่าน Chairperson นะครับผู้ช่วยศาสตราจารย์ดร.นิธิรุ่งธนาภิรมย์นะครับจากภาควิชาคณิตศาสตร์และวิทยาการคอมพิวเตอร์คณะวิทยาศาสตร์จุฬาลงกรณ์มหาวิทยาลัยครับ
The first session will be led by our chairperson, Assistant Professor Dr. Nithi Rungthanapirom from Faculty of Science, Chulalongkorn University. Please welcome him with a big round of applause.
ขอเสียงปรบมือด้วยครับ
Hi, good morning, everyone. It's my great honor to be a chairperson here and to introduce my advisor, Professor Jakob Stix. He used to be my PhD advisor as I was studying in Frankfurt. But beforehand, we got to know each other already in Heidelberg. I think I will not say that much, and we will give him more time for his stuff. He will teach us about Abelian varieties or finite field as a category of modules. So please enjoy.
Thank you very much for the warm welcome, for the hospitality, and I really enjoy the conference so far. Thank you also for hosting me in Chulalongkorn University for 10 days, Niti. It was a tremendous pleasure to be there. Thank you. So, yeah, wrong direction. My talk will be about Abelian varieties over finite fields, and I'd like to explain to you that although this is a geometric theory, you can describe it in terms of a category of modules, so just algebra. Here's the plan. So the first 3 sections will familiarize you with the subject over the complex numbers and show you that there a linear algebra description of these categories is possible. In section 4 and 5, I'm going to tell you more about the specialties when everything is transformed to happen over a finite field, which might sound strange to you at first. And in the last section, I'd like to explain to you some results that we have. So all of this is joint work with Tommaso Centelege, who is in Heidelberg. So let me start by telling you the one-dimensional case. You've heard of elliptic curves, probably. These are connected proper smooth algebraic group schemes of dimension 1. It doesn't matter if this doesn't sound familiar to you. Important is that these elliptic curves, they can be written as cubic plane curves. So there's, after projective linear change of coordinates, just a very simple equation, y squared equals x cubed plus a constant x plus another constant. So these are just cubic equations, and the distinguished point here has been disappeared to infinity. The topology of these is very easy. This is just to be visualized as a donut. The picture over the complex numbers here I've taken from Wikipedia, which is a very good source for these pictures. And if you look at the same equation over the reals, depending on the parameters, you get either 2 connected components or just 1 connected component. And the point at infinity is kind of where these lines, which have, where this is now closed, heading up towards infinity. An important word in the definition was group. These objects are groups, and here's a picture that should remind you, in case you already know, about the group law and how this comes about. This is a very nice gem of Diophantine mathematics. If you have a cubic equation and you take 2 points, say P and Q here on the first picture, then in the plane there's always a unique line through these 2 points. And then let's say we have chosen a parameter T for this line. When you restrict your cubic to this line, then it becomes a cubic polynomial in this parameter T. Now, the solutions of that cubic polynomials corresponds to the intersection points of the cubic, which is red, with the line, which is blue. And you fortunately, because you designed the line to pass through 2 points that you already know 2 solutions. Which means that by Vieta, where you're summing the solutions gives you 1 coefficient of the equation, you can easily, from the equation, compute the 3rd point. And this 3rd point is canonically associated to this pair P and Q. And it would be nice if this would just be the sum of the 2 points, but it happens to be the negative of the sum. But this is just an extra annoyance, but it's still geometry. So you get a group law basically on this principle that in a cubic polynomial, if you know 2 solutions, you know the 3rd. Now, elliptic curves, they're at the crossroads of various mathematical areas, and therefore many people get in touch with them from different perspectives, and that makes them a beautiful subject to study. For me as a number theorist, it's more important, instead of these geometric pictures that I showed you, that I'm able to also consider them as equations over, let's say, the rational numbers, and then a cubic equation which is very famous is this x cubed plus y cubed equals z cubed, which is the Fermat equation for exponent 3, where Fermat claimed that there's, famously, that there's no non-trivial solution in the integers or the rational numbers. And for exponent 3, this is a theorem due to Euler. And in essence, it says that this elliptic curve only contains the rational points, so solutions with rational coefficients, which are given when one coordinate is 0. The picture which explained the group law, although it appealed to your real geometric intuition, it actually holds over any field. Because if you remember the explanation I gave by saying the sum of the roots is the coefficient in this polynomial, then everything was algebraic. So it doesn't address to geometry at all. And therefore, the set of solutions of such an elliptic curve E over any field K is still an abelian group. Now, for this abelian group, there have been famous results due to Mordell, and Weil did the higher dimensional case actually. The group over any number field will be a finitely generated abelian group, so is some free part with some rank, which the famous Birch-Swinnerton-Dyer conjecture is talking about, and some finite group. Now, we are more interested in the case of a finite fields in this talk. A finite field, you can think of just the integers mod p, so z mod p, or you know that for every prime power q, there's a unique finite field of that order. And if you plug in, this is coefficients for your equation, so the equation has to make sense over that field, of course, then you get a finite group. Simply because on a finite field, you have only finitely many values for your variables that they can take off, and this is zero knowledge proof that there is a finite group. So now this finite group plays important roles in elliptic cryptography. And here on my German national ID card, there is an algorithm based on an elliptic curve which makes this more secure, I hope. So this has applications in the real world. Another famous theorem I wanted to tell you is this theorem of Hasse, and in the higher dimensional case, Weil. If you count the number of solutions and you compare it with sort of the vacuous equation, which gives you as a curve the projective line, which has q plus 1 solutions, then the difference is an order of magnitude 1/2 less in the parameter q than that. So the number of solutions is confined to an interval of length 4 times square root of q. Now, over the complex numbers, if you remember your course on complex functions, there is this discussion of the Weierstrass P function for doubly periodic functions on the plane. So you start with a period lattice, you pick 2 complex numbers, omega 1 and omega 2, and you span the integral multiples of that in the plane. You get a grid which covers the whole plane with a fundamental domain, which is just this parallelogram. And then you're asking if there's a doubly periodic holomorphic function. Okay, holomorphic doesn't work because that would be bounded on the whole plane, but Liouville, this would be a constant. That's too boring. We have to allow some poles, and it turns out that the Weierstrass P function, where you're summing over essentially 1 over z minus a lattice point is squared, gives you a doubly periodic function, which is fundamental for this lattice. You have to have some correction factors summoned here because you want this to be convergent. And if you take the derivative, which is written here, it's clearly visible that this is a periodic function because this is basically the pole of order 3 at the origin and then shifted along the lattice so that it's automatically become periodic, doubly periodic. And you can use this function and also its derivative to give a new description of your elliptic curve where you're starting with the complex numbers you map it to the quotient modulo this lattice, so you basically get this parallelogram where you're wrapping around parallel sides, and so this in your head should now form the shape of a torus, a donut, and yeah, so this is this shape, and since these functions are doubly periodic, they define a well-defined map to the solutions of this cubic equation, which describes an elliptic curve. And now it turns out that this elliptic curve is actually isomorphic to the C mod lambda, and this shows that this cubic equation actually gives you geometrically a donut as its shape. Okay. Now, we would like to have first a more intrinsic description of this picture, because here we've made too many choices for my taste. So this is a quick detour to the complex geometry and Hodge structures. This is not essential for the main purpose of the talk, which is over finite fields, but let's quickly go through this. There's the Abel-Jacobi map, which associates to a pointed elliptic curve this line integral over a choice of a line from the origin to the point, and then you're integrating a differential form. This produces a linear form on the space of all differentials, because we evaluate an integral over that, but it's not well defined. Because I made a choice of a path linking the origin to this point, and if you take a different path, in an elliptic curve, this might not be contractible, and therefore the integral over a closed loop need not vanish, as in the complex plane it does, fortunately. So there's some ambiguity involved, and that is exactly captured by the period lattice that I explained to you before. So what does this data use? It uses the lattice, which is given by singular homology. Actually, it's dual in terms of cohomology. And then the de Rham isomorphism pairing, which compares singular cohomology with de Rham cohomology, so the cohomology which is built by differential forms. And then on de Rham cohomology, because this is a complex projective variety, there is, using Delbourg resolutions, a description of cohomology in terms of holomorphic differentials and anti-holomorphic differentials. And if you count how many holomorphic differentials you use to describe your cohomology, this gives you a descending filtration, which is called the Hodge filtration. And here in this case, there's only one step, and the step that you get is exactly the global differential forms on the elliptic curve, which means this is basically just dz, if z is your complex coordinate in this description where this was C modulo lattice. And okay, so this is the data. It looks like linear algebra data to me. So it's a lattice and it's a vector space. It's a filtration on that vector space. And as we've seen before, or in the first line here, this is able to recapture the elliptic curve. So the message from this slide is, due to Riemann, so already 200 years ago, almost, linear algebra data in terms of a lattice and a Hodge filtration. So lattice and something which is sort of geometry at infinity recovers the elliptic curves. And actually Abelian varieties, which I haven't talked about so far, although it's in the title, they do exactly the same. And then the more fancy description is that this is equivalent to polarizable integral Hodge structures of weight 1. But it's still just linear algebra in the sense I explained. So since this is a talk about Abelian varieties, I should at least at some point say what an Abelian variety is. So an Abelian variety is just the same thing as an elliptic curve, but without the constraint on the dimension. So it's a connected, proper, smooth algebraic group scheme and no constraint on the dimension. And again, it's not important that these words say anything to you. Important, it's a group, it's algebraic, and you can show that it's commutative, and this is very fitting because Niels Henrik Abel was among the first to study this structure, although he of course did not call these Abelian varieties. but this is a picture of Abel. And now these are abelian varieties in his name. They're also commutative, so abelian, so everything is very fitting nicely. Okay, I said in dimension 1 we just revisit elliptic curves, and over the complex numbers this now becomes a higher dimensional version of a donut, which just means you take topologically the sphere and take 2g, so twice the dimension of copies of S1 and take the product of those. Also here we have a complex uniformization by some g-dimensional vector space. So complex, geometrically speaking, these look like g-dimensional complex vector space divided by a lattice, so this becomes compact. And then there's a hot theoretic description, but we don't care. Now, this talk is about abelian varieties over finite fields, and therefore it is important to highlight a few things that hold in general for categories of abelian varieties. And essentially, this is all you need to know about abelian varieties in the end, because this sets sort of the problem at hand that we try to solve. So you can treat this over any field. It was easier to see this for elliptic curves, because there I talked about a cubic polynomial, and cubic polynomials can do over any field. Here, unfortunately, in the higher dimensional case, there are no typical equations, so equations for these things become much harder. It's better to work really with algebraic geometry. So here are the features of the category of all of them over a given field. It's an additive category, which means that the spaces of homomorphisms between them are abelian groups, and the composition is distributive. More precisely, the space of homomorphisms between two abelian varieties is a free abelian group of rank, which is bounded in terms of the dimensions. So in some sense, you can say that these homomorphisms are lattices. Okay, an important notion is the notion of an isogeny, which means we are looking at things which are finite, so finite fibers, and surjective. And this kind of means replacing an abelian variety by something which is very close. And Poincaré has shown if we are allowing formally to invert these isogenies, so in some sense we are replacing the lattices by Q-vector spaces because we only need to invert multiplication by the integers, then suddenly every sub-object has a complement. Now, if you think about a category of modules, and this is where we're ultimately heading to, if you're in a category of modules where every submodule has a complement, then you're really happy, because then you're in a semi-simple situation, and every module is simply, in a non-canonical way, a direct sum of simple ones, and so you can pile up the simple ones together, and you get an isotypical decomposition. So if you do linear algebra and have a semi-simple operator, you will decompose it into eigenspaces, and this is the decomposition into the isotypical components. And a one-dimensional vector space where you're acting with the complex eigenvalue is sort of the simple case. So this category of abelian varieties, although it has a fancy geometric definition at first, it turns out if you do this kind of almost harmless operation of inverting the integers to the rational numbers, then it becomes a very, very easy category where everything is just given by a multiple of simple objects and sums of those. Which means that the endomorphism rings of these objects are semi-simple Q algebras. So something which is algebraically well understood. Now, this sort of gives me a description of the category up to inverting isogenies, but I'd like to have a description of the whole category without doing this, so on the integral level. What does this amount to? I first have to classify what are the simple objects, and secondly, we have to understand what these endomorphism algebras are, and As a third step, and this is where we really deviate from just knowing the category up to isogeny to the honest category, is we have to sort of distinguish which are these lattices of homomorphism spaces inside these rational vector spaces, right? So the whole problem, although it's phrased in terms of arithmetic of abelian varieties, it essentially comes down to pinning carefully down lattices in Q vector spaces. Okay, technically this becomes a bit tricky because if you remember what we did of the complex numbers, there was this lattice that was key. This was a free abelian group, and it was embedded in the complex vector space, and that sort of recovered the abelian variety. Now here, over a finite field or a general field, we do not have this lattice, right? The lattice is homology. This is done using walking around in paths on your space, but over a finite field, this space maybe more looks like a bit of dust. It's lots of finite points and not really connected. So there's no real paths, so we don't have homology at our disposal. Fortunately, Tate came up with a way to replace this, at least approximatively, by looking at the Tate module. So the Tate module of an abelian varieties looks at L to the n torsion for some prime number L and assembles this in a nice fashion so that you get something which looks like your lattice but L-adically completed. Right? So you get back the lattice tensor ZL but not the lattice inside. Right? And as a group, this Tate module is just a free ZL module of rank twice the dimension. So, and okay, so you might now be unhappy because you don't have your lattice, but you should be very happy because you gained something else instead. Namely, you gained Galois action. This Tate module is built by finding points in algebraic extensions of your base field, and therefore the symmetries of field extensions, so Galois groups, will act on this. And these are the famous Galois representations attached to abelian varieties or elliptic curves, which Wiles used in his proof of Fermat's theorem. So this is at the base of a lot of modern number theory, or the Langlands program and things like that. Over a finite field, there's just an action Frobenius. And this is a shout out to the group of students from Khon Kaen University where I gave my course last days. I told them that Frobenius is everywhere. And this is another instance where Frobenius is everywhere. Now, here's a theorem of Tate, which says that actually this L-adic lattice is already very good in talking about the space of homomorphisms. So recall, this is a Z lattice that we are trying to control precisely. And this theorem at least tells us if we L-adically complete, we have complete control about this lattice. Okay, two more important objects in this talk. Any abelian variety in characteristic P has an extra symmetry. This symmetry is a Frobenius symmetry. Namely, if you raise your points to the qth power, and Q is the cardinality of the field over which you're working, because Frobenius is a field isomorphism, so for example, if Q would be 2, this would be the infamous equation A squared plus B squared is A plus B brackets squared, which we are not allowed to teach in school, but in characteristic 2 it's true. So, the qth power Frobenius is just a more jazzed up version of the same. So that gives us an extra symmetry that all of these objects have, which is very nice, and we will benefit from it. So this extra symmetry acts on this Tate module, and it will have eigenvalues, and these eigenvalues, kind of the spectrum of Frobenius of that abelian variety, consist entirely of Weyl Q numbers. Now, what are Weyl Q numbers? These are algebraic integers which are too good to be true. They are in such a way that all complex conjugates have the same absolute value. Usually, if you take an algebraic number under the embedding into various embeddings into the complex numbers, the conjugates will have very different absolute value. But these here, they all have the same absolute value, and this means that the complex conjugate number is always q divided by the number, regardless of which complex embedding you take. Now, recall there was this program where we first had to distinguish what are the simple objects and what are the endomorphism algebras of that simple objects. And this actually, up to isogeny, has been carried out by Honda and Tate. And the answer is as follows. So the simple objects, so the building block of the theory, they are in one-to-one bijection with these Weil Q numbers up to conjugation. So up to conjugate, Galois conjugate algebraic integers. How does that go? That association, you take a simple object, then because in a semi-simple category for a simple object by Schur's lemma, the endomorphism is always a skew field. And recall we have finite dimension over Q, so this will be a skew field with center a number field. So on the right-hand side, although it looks like an abstract categorical notion, this endomorphism of a FQ of this simple object B and then tensoring it up to Q, what's written there on the right is a number field, is a division algebra over a number field. And if we assign to this Abelian variety its geometric Frobenius endomorphism, this is an element which actually, because Frobenius commutes with everything inside, lies in the center of this endomorphism ring. So this guy lies in a number field. And although it looks like a map, I can treat it as an algebraic number, right? Because in my definition of a number field, I'm not talking about subfields of the complex numbers, as some people do. For me, an algebraic number, a number field is just a finite extension of Q. So it need not be a priori embedded into the complex numbers. And I'm taking benefit of this here. The right-hand side contains as a center a number field. I describe you an element in the center, so I have given you an algebraic number. You need to prove that this is an integer, and you need to prove that its eigenvalues are Q-Weil numbers, and then you need to prove that this is actually bijection. But you don't need to prove this. Honda and Tate had proven this for you. Okay, once this is set up, pi will always denote a Weil Q number, and I need a notation for a simple Abelian variety which goes under this address. So B pi is the Abelian variety whose spectrum of Frobenius is given by this algebraic integer pi. Now the endomorphisms, as I said, by Schur's lemma, this is a skew field with center a number field, or more fancy, it's a central simple algebra, and the center turns out to be exactly generated by this Frobenius. So this is the number field generated by this Weil number pi that is in the game. And now you need to pin down what is this element, what is this skew field. And now this is a reference to the course at Chulalongkorn University, because there we had the famous local global principle by Hasse, Brauer, and Noether, which said that these guys are uniquely determined by their local invariance. And so here's a formula for the local invariance that Tate computed, and this uniquely determines this algebra. So it's a bunch of numbers. We know that they sum up to 0. You can't see this here, but they do. And these numbers, they describe an algebra in a unique way. So this means that with this theorem, basically, part 1 and 2 of the program of describing this category of Abelian varieties is already done. Now, with Frobenius comes Verschiebung. Verschiebung is a German word, and it actually is the terminology for actually this morphism. So it has found its way in there. So there's a duality in the field. So you pass to a dual abelian variety, and the dual Frobenius is actually Verschiebung. And in terms of these simple abelian varieties, it will be just multiplication by Q divided by Frobenius, which a priori is unclear whether this gives you a morphism, but the theory of Verschiebung tells you that this is also a morphism of abelian varieties. And so now we have not only Frobenius, but also Verschiebung as something which is an additional symmetry of these objects. And now here comes a great theorem by Professor Deligne, one of his first papers, I think, which describes a certain category of abelian varieties in terms of linear algebra data. So this is kind of the model theorem that we are after. Namely, you describe them in terms of what's now called a Deligne module. A Deligne module is just a lattice. And now we are adding linear algebra data, an endomorphism, call it F for some reason. And you ask this endomorphism to be semi-simple when tensored over Q as an endomorphism of the Q vector space underlying the lattice. And all eigenvalues should be just ordinary VQ numbers. This endomorphism has to have the additional property that if you take Q divided by the endomorphism, this should preserve the lattice. This is some integrality constraint on what endomorphisms are allowed. And now this data by the theorem of Deligne actually describes an equivalent category to the category of just the ordinary abelian varieties. Now highlighting the ordinary is important. Ordinary means that these are abelian varieties which are most similar to the abelian varieties that happen over the complex numbers. And in fact, these are really the generic ones, but not all of them. And actually, the other ones, the non-ordinary ones, are the more interesting ones where there's more arithmetic involved. So the precise meaning of ordinary is not that important. So you take the Abel number pi as ordinary if it's minimal polynomial that always has this kind of symmetric shape skewed with powers of the size of the residue field. So you see it's not palindromic, this polynomial, but up to certain powers of Q that you have to invest. And then there's the middle term, and the middle term is the crucial one for ordinariness. If this is not divisible by P, then this is ordinary. And from this description, you see that this is more the generic behavior. Okay, we're coming closer to results. Now, if we restrict our category of abelian varieties to those abelian varieties where only the simple parts belong to a set of finitely selected Weil numbers, then this will be an easier category to describe. There's a ring, call it LW, which is just the image of this quotient of this polynomial ring in variables f and v, with the only relation that f times v has to be q in this product of these number fields, which give rise to the Weil numbers in W. And this ring turns out to have a very easy description. You just have to add one more equation, and this is this symmetric polynomial that you get from the minimal polynomial by basically substituting x for f, dividing by x to the d, and also plugging in that v equals q to f over f, and then canceling all these powers of q here that are there. So this basically is the ring which encodes the action of Frobenius and Verschiebung, and will enhance the category to a linear category over this ring. And then here comes the first result. If you consider the prime field Fp as a base, then, and you consider that the square root of p is not among your Weyl numbers, then actually your category of abelian varieties truncated with that list of Weyl numbers is isomorphic to a category of modules under that ring, and their functor which transposes from abelian varieties to these modules is a representable one. And yeah, the modules have to be lattices, right? Because the right-hand side is a Hom space, so it's a lattice. And here's a list of people who have worked on similar problems. For a matter of time, I should not read them out loud, although they deserve praise for their work. If you replace p by q a power, then you basically get the same result, but it's more complicated. You again have a representable functor to now a category of modules over something which is a non-commutative ring, and where I don't have any explicit equations to write it down. And also the size of the lattice unfortunately has increased, so there's an extra factor of 2 times r, where r is the exponent in q equals p to the r. So this is my final slide, and this is actually why I'm fond of the result and why I think this is fun. So we started with a category of abelian varieties over a finite field, so this is geometry of a very complicated nature, and we've transformed it by suitable Hom functors to a category of modules. Now, as an arithmetic geometer, when I see modules and rings, I always take the spectrum, which is a jazzed-up version of the spectrum of Frobenius that I talked to before. So this ring RW describes a curve cut out by this one equation on this normal surface, which is given over the integers by 2 coordinates f and v, which multiply to q. So in some sense, the geometry fibers over the collection of prime numbers, and there's 2 special divisors, namely where the Frobenius is 0, f, and where the Verschiebung is 0, and they happen to live over the fiber over the prime p, and they intersect in the supersingular point. This is where f and v is 0. Now an abelian variety is a module under spec over Rw, so it becomes a sheaf which is almost locally free, which is supported on this blue curves, which is the spectrum of this ring. And so in some sense, these curves grow and become more and more when you're looking at larger and larger sets of Weyl numbers. And your abelian varieties now spread out over these curves. And if you want to study them in classical terms, for example, the Tate module, then what you're doing basically is you're looking analytic locally in the neighborhood of where these curves cross the line where you have the prime number L. And when 2 of those curves intersect, you get congruences on these Weyl numbers that play a role. And last fact, the abelian variety is ordinary if and only if it does not pass through the supersingular point, because the defining equation that you have, the value at the supersingular point is exactly this middle coefficient. So you're passing through the supersingular point if and only if this middle coefficient is divisible by p. So this picture, although it looks like a funny drawing, it actually allows you to organize the arithmetic algebraic information contained in this category in terms of geometry spread over this arithmetic surface. Thank you very much. Thank you for your attention.
Yeah, thank you very much for the enlightening talk. Yeah, we have some time for the questions, if there are any. Okay. Yeah. Maybe I ask you something. So you talk about the isogeny in like in section 3 or something, and Yeah. So what's the idea like? So the idea of isogeny is something like to you consider the group of morphisms as cleavator spaces or
So the idea of isogeny is that so we have invariants like these lattices, but working over the integers with modules is much harder than working over a field where you just have vector spaces. So as a first approximation to study your category, you want to formally invert from the integers to the rational numbers. So you basically tensor all Hom spaces with Q. And what this geometrically refers to is that a map which is multiplication by n should now become formally invertible, because you also have the map 1 over n, which is not a real map, but a formal map. And this multiplication by n is sort of the epitome of such an isogeny. So these isogeny, if you think about complex analytically, they are just topological finite covers. And actually the picture here with the period lattice, that already contains kind of, with these subdots, this is the lattice that you get by taking the multiplication by 4 isogeny. So you get a smaller lattice. If you should get a larger lattice to get, so we have to reverse it. So the dots filled in here, they describe something, and then the original bigger grid describes something below, and the whole thing is the multiplication by 4 map. So you get a topological covering, and so in some sense you're looking at your invariant only up to commensurability. So it's something that makes life easier in a lot of ways, and you can find your original problem as embedded in there, and then you only have to deal with finding lattices in Q vector spaces. That's the purpose of these isogenies. Thank you for the question.
Thank you.
I have a question for.
Yeah, sure.
I have a question about this. I have seen the theory of Satet theory about the equivalence of category between Abelian schemes and p-divisible group. I was wondering if there lies some sort of connection to the Honda-Tate theory.
Yeah, thank you very much. Actually, the theory of p-divisible groups is exactly what happens near these purple part of the diagram. If you want to understand the Hom spaces of Abelian varieties there, you have to do Dieudonné module theory. And I was sweeping all of this under the rug here, right? But you're exactly right. So this is what happens there.
Thank you very much.
Actually, we have a few more minutes for questions if there are any. Okay. Yeah, it seems not to be the case, so let's thank the speaker again.
ครับขอกราบขอบคุณท่านวิทยากรแล้วก็ท่านแชร์เพอร์ซันเป็นอย่างสูงครับในโอกาสนี้นะครับขอกราบเรียนเชิญท่านศาสตราจารย์ดร.วิเชียร ลหโกศลนะครับขึ้นสู่เวทีนะครับแล้วก็ขอเรียนเชิญท่านอาจารย์นิธิขึ้นสู่เวทีด้วยครับ
Let us thank our keynote speaker and chairperson for this wonderful session. Next, may we have the honor to invite Professor Dr. Vichian Lauhakoson, another chairperson on stage.
ครับ เรามีของที่ระลึกเล็กๆน้อยๆให้กับท่านวิทยากรแล้วก็ท่านแชร์เพอร์ซันนะครับครับในโอกาสนี้ขอเรียนเชิญท่านวิทยากรรับมอบของที่ระลึกครับมีไดโนเสาร์น่ารักนะครับขอเสียงปรบมือด้วยครับครับขอบพระคุณมากครับในลำดับถัดไปนะครับขอกราบเป็นเชิญท่านแชร์เพอร์ซันรับมอบของที่ระลึกครับครับเรามีไดโนเสาร์ด้วยนะครับไดโนเสาร์ผูกคอครับขอเสียงปรบมือด้วยครับขอขอบพระคุณทุกท่านเป็นอย่างสูงนะครับท่านวิทยากรท่านแชร์เพอร์ซันแล้วก็ท่านศาสตราจารย์ดร.วิเชียร โลหะโกศลนะครับครับเราครับขอขอบพระคุณทุกท่านมากๆครับ